Imagine you want to describe the moon, not just say, it's that big bright thing in the sky. I mean, truly describe it so that someone, somewhere else in the universe could build a perfect copy. Where would you even begin? A good place to start would be its surface. It's covered in craters, each one a scar from a long ago impact. To describe just one crater, you would need a list of numbers. You would need its location, perhaps using latitude and longitude, just like on Earth. Then you would need its size, its diameter, and what about its depth? That's another number. Already we have a handful of numbers for just a single crater, but the moon doesn't have just one crater. It has hundreds of thousands of them that we can see from here. And if you got closer, you would see millions more smaller ones. Each and every one needs its own set of numbers. The list would grow very quickly. We would have numbers for the location, size and depth of the crater Tycho, then another set for Copernicus, then another for every tiny pockmark that our best telescopes can find. The list of numbers would become enormous, stretching for pages and pages, and we have only just begun to describe the surface features. It's a monumental task, a cosmic puzzle of endless pieces. Now, think about the material the moon is made of. It's not all the same. The dark patches, the Luna Maria, are different from the bright highlands. To describe these, you would need more numbers. You would need to detail the chemical composition of the rock in every single place. What percentage is silicon? How much iron is there? What about oxygen or titanium? You would need a new set of numbers for every square meter of the moon's surface. This information tells the story of the moon's violent past, how it formed and evolved. The numbers aren't just data, they are the language of the cosmos, telling a story written in stone and dust. So the number of numbers we need is exploding. We started with a few details for one crater, and now we are trying to catalogue the chemistry of an entire world. And we haven't even mentioned the mountains, the valleys, or the exact temperature at every point on the surface, which changes dramatically from day to night. To truly perfectly describe the moon in all its glorious detail would require a practically infinite list of numbers. It's a beautiful, complex and messy object, just as we would expect a world to be. Its complexity is what makes it interesting. It's a testament to the rich history of our little corner of the solar system, all written in numbers. The moon might seem complex, but it is a relatively simple world. It has no atmosphere to speak of, no oceans and no life. Now let's turn our attention to a planet like Earth. The list of numbers needed to describe our own world would be truly staggering. You would have to map every mountain and every deep-sea trench, just as we did for the moon's craters. But then you would need to describe the atmosphere. What is the pressure, the temperature, the wind speed and the humidity at every single point? From the ground all the way to the edge of space? The weather is constantly changing, so your list of numbers would need to be updated every single second. Think of the oceans. To describe them, you would need to map the currents, the temperature, and the salinity at every depth all across the globe. That alone is an immense amount of information, and we haven't even talked about life. How would you describe a rainforest? You would need to catalogue every tree, every insect, every bacterium. You would need to describe its genetic code, its position, its behavior. The number of numbers required to fully capture a planet teeming with life like Earth is, for all practical purposes, infinite. It's a level of complexity that makes describing the moon seem like a child's puzzle. Each planet, each world is a universe of information in itself. And what about a star like our sun? A star is a giant ball of fusing plasma. It might look like a simple, perfect sphere from a distance, but up close it is a chaotic and violent place. To describe it, you would need to know the position and energy of every single particle within it. There are more atoms in the sun than there are grains of sand on all the beaches on Earth. Trying to list the properties of every single one is an impossible task. You would also need to describe its powerful magnetic fields, which twist and snap, creating solar flares and immense eruptions. The complexity is mind-boggling, so we see a pattern emerging across the universe. Things are messy, they are complicated. From moons to planets to stars, every object is defined by a colossal amount of information. Each one has a unique history, a unique structure, and a unique chemical makeup. This complexity is what we study. It's what astronomers and physicists spend their lives trying to understand. The universe, it seems, is built on an almost endless foundation of details. You need a vast, perhaps infinite number of numbers to describe almost anything out there. That is, until you come to a black hole. Now, let's consider one of the most extreme and mysterious objects in the entire universe, a black hole. A black hole is what's left behind when a truly massive star dies and its core collapses under its own gravity. It is a region of space-time where gravity is so strong that nothing, not even light, can escape. Given how extreme they are, you might expect that describing a black hole would be the most complicated task of all. You might think you'd need even more numbers than you would for a star or a planet, but something amazing and deeply strange is true. The exact opposite is the case. To completely describe any black hole in the universe, you only need 3 numbers. That's it, just 3. The first number is its mass. This tells you how heavy it is, which in turn determines the size of its event horizon, the point of no return. A more massive black hole has a stronger gravitational pull and a larger event horizon. This one number tells you the most important thing about the black hole's influence on the space around it. It's the primary characteristic, the one that governs its power over passing stars and light. The second number you need is its electric charge. In theory, a black hole could have a positive or a negative electric charge, just like an electron or a proton. However, we think that most black holes in the real universe will have a charge that is very close to 0. This is because if a black hole did have a significant charge, it would quickly attract particles with the opposite charge and become electrically neutral. Even so, the possibility is there, so charge is one of the 3 fundamental properties that a black hole is allowed to have. It is a part of its fundamental identity. The final number is its spin, or more precisely, its angular momentum. Just as a spinning star collapses to form a black hole, the black hole itself can continue to spin, and it can spin incredibly fast, sometimes approaching the speed of light at its event horizon. This spin doesn't just make it bulge at the equator, it actually drags the very fabric of space-time around with it. This effect, known as frame dragging, is one of the most bizarre predictions of Einstein's theory of general relativity. So with just these 3 numbers, mass, charge, and spin, you have a complete description of the black hole. This shocking simplicity of black holes is summed up by a famous idea in physics with a very memorable name, the no-hair theorem. The theorem states that black holes have no hair. The name was coined by the physicist John Wheeler, and it's a metaphor. The hair represents all the other complex details that an object could have. Think back to our moon with its millions of craters, mountains, and different types of rock. All of that is hair. Think of the Earth with its swirling weather patterns, its oceans, and its incredible biodiversity. That is an enormous amount of hair. All of that intricate, detailed information is what gives an object its unique character. The no-hair theorem says that black holes are bald, that they have no complex features. Once a black hole forms, it loses all the intricate details of whatever it was made from. It doesn't matter if the black hole was formed from the collapse of a star made of hydrogen or a star made of helium, or if it was made by throwing 1 billion encyclopedias into a gravitational singularity. The final black hole will be exactly the same as long as it has the same mass, charge, and spin. All the information about the original material, its chemical composition, its texture, its temperature, is completely and utterly wiped away. This is profoundly different from anything else in the cosmos. If you have 2 stars with the same mass, they can still be incredibly different. One could be a young hot blue star, while the other could be an old cool red giant. Their chemistry, their age, their temperature, all these details make them unique. But if you have 2 black holes with the same mass, the same charge, and the same spin, they are not just similar, they are identical. They are indistinguishable from one another in every single way. There is no way to tell what they were made of. This idea is one of the most elegant and unnerving in all of physics. It strips away all the wonderful complexity we see in the universe and reduces these cosmic titans to just 3 numbers. It's as if the universe has a rule that says when gravity becomes this strong, all the messy details must be shaved off, leaving behind only the purest and most fundamental properties of mass, energy, and motion. This cosmic shave is what makes black holes so simple, but it also opens up one of the deepest paradoxes in modern science, a question that strikes at the very heart of reality itself. So, if a black hole erases all the complex information of the matter that falls into it, we have to ask a very serious question: where does all that information go? In physics, there is a fundamental principle that states that information can never be destroyed. This is a cornerstone of science, as basic as the idea that energy cannot be created or destroyed. Information, in this sense, is the complete description of a physical system. It's the list of numbers we talked about for the moon or for a star. It tells you everything you need to know about the state of every particle. The laws of physics suggest this information must always be conserved, but black holes seem to violate this rule. Imagine you take this essay, a wonderfully complex thing full of information, and you burn it. You might think the information is destroyed, but it isn't, not really. A physicist could, in principle, collect all the smoke and ash and heat, and by measuring the state of every single particle, they could reconstruct the original essay. The information is just scrambled, not lost. It has been converted into the intricate dance of countless atoms and photons. It would be impossibly difficult to do, but according to the laws of physics, it is possible. The information is still out there in the universe. Now, what happens if you throw the essay into a black hole? According to the no-hair theorem, the black hole's mass will increase a tiny bit, and maybe its spin will change slightly. But the information contained within the words and sentences of the essay seems to have vanished completely. The black hole is described only by its mass, charge, and spin. There is no trace of the essay's content left. You can't examine the black hole and figure out what fell in. Whether it was an essay, a diamond, or a bucket of water, the end result is the same. The information appears to have been permanently deleted from the universe. This is what physicists call the black hole information paradox. It creates a direct conflict between two of our most successful theories. On one hand, Einstein's theory of general relativity predicts the existence of black holes with their no-hair simplicity. On the other hand, the laws of quantum mechanics, which govern the world of particles and information, insist that information can never be lost. They cannot both be right as they currently stand. This isn't just a small disagreement, it's a fundamental contradiction that tells us we are missing something profound about how the universe works at its deepest level. The black hole information paradox forces us to confront the limits of our own understanding. It suggests that our current theories of physics are incomplete. They work brilliantly in their own domains. General relativity for gravity and large structures, and quantum mechanics for the very small. But when you get to a black hole, these two worlds collide. To solve the paradox, we need a new theory. A theory of quantum gravity that can unite them and describe what happens when immense gravity meets the quantum world. This is one of the greatest challenges in science today. So, what could be the answer? Scientists have proposed some fascinating, mind-bending ideas. One idea is that the information isn't lost at all, but is somehow stored on the surface of the black hole, on the event horizon itself. In this picture, the event horizon acts like a two-dimensional hologram, containing all the information of the three-dimensional objects that have fallen in. It would be scrambled and encoded in a way we don't yet understand, but it would be there. This holographic principle suggests that our entire universe might be a projection from a distant lower dimensional surface. A truly strange thought. Another possibility, even stranger, is that the information falls into the black hole and passes into another universe. Perhaps black holes are gateways, bridges to other realities that are completely disconnected from our own. Or maybe the information simply goes to a region of space-time where our laws of physics break down completely. The singularity at the center of the black hole, a point of infinite density where space and time cease to exist as we know them. The truth is, we simply do not know. These are the questions that keep physicists awake at night, staring into the cosmic darkness. The humble black hole, an object defined by just 3 simple numbers, has become a key to unlocking the deepest secrets of reality. It challenges our most basic assumptions about space, time, and information. By trying to understand what happens to a simple piece of paper when it falls past the event horizon, we are forced to ask questions about the very fabric of the cosmos. The answer, whatever it may be, will undoubtedly lead to a new revolution in our understanding of the universe, revealing a picture of reality that is likely far stranger and more wonderful than we can possibly imagine.